From the moment of its fiery birth, the universe has been on an unstoppable journey. A journey of expansion, evolution, and ultimately, an inevitable end. But what will that end look like? Will it be a whimper or a bang? For centuries, humanity has gazed at the stars, pondering our origins. Today, we turn our gaze to the distant future, to the ultimate fate of everything we know. Our understanding of the universe's destiny is intrinsically linked to its fundamental properties, its density, its expansion rate, and the mysterious forces that govern them. For a long time, cosmologists considered three primary scenarios, each painting a dramatically different picture of cosmic demise. Let's begin with perhaps the most widely accepted and chilling scenario, the Big Freeze, also known as heat death. Imagine a universe where stars, one by one, burn through their fuel, their once brilliant light fading into an eternal twilight. Galaxies, once vibrant beacons, become vast graveyards of black holes and neutron stars. In this future, the universe continues to expand, but its energy becomes ever more dispersed. Entropy, the measure of disorder, reaches its maximum. There are no more temperature differences, no more energy gradients to drive any process. All activity ceases. Even black holes eventually evaporate through Hawking radiation, leaving behind only a sea of photons and fundamental particles spread so thin that interactions become almost impossible. It is a universe where time itself loses its meaning, a state of absolute, eternal stillness. But what if the expansion of the universe isn't just constant, but accelerating at an ever-increasing rate? This brings us to the terrifying concept of the Big Rip. Our universe is permeated by a mysterious force known as dark energy, which is responsible for the observed acceleration of cosmic expansion. If the density of dark energy were to increase over time, or if its repulsive nature were to strengthen, the consequences would be catastrophic. The Big Rip wouldn't just tear galaxies apart, it would tear everything apart. First, distant galaxies would accelerate away from each other at speeds exceeding the speed of light, effectively disappearing from each other's observable universe. Then, as the dark energy's influence grew even stronger, gravity itself would be overcome. Galaxies would unbind, stars would be ripped from their orbits, and eventually, even atoms themselves would be torn asunder, leaving behind a cosmos of isolated, fundamental particles, unable to interact, unable to form anything. A complete and utter dissolution of reality as we know it. For a long time, the Big Crunch was the favored hypothesis, a poetic symmetry to the Big Bang. Imagine the universe, having expanded for billions of years, finally reaching a critical point where its own immense gravity begins to pull everything back together. The expansion slows, then halts, and then reverses. First, just slightly, as the vast, cold emptiness of intergalactic space compresses. Then, violently. The cosmic microwave background radiation, the ancient echo of creation, is blue-shifted, its wavelengths compressed until it becomes a visible glow, then a searing, blinding torrent of X-rays and gamma rays. Stars, long dead, are vaporized. Black holes, the titans of the old universe, begin to merge in a final, chaotic dance, growing to unimaginable sizes before they too are devoured by the collapsing cosmos. In the last, fleeting moments, the universe becomes a single, apocalyptic furnace. All structure is annihilated. Atoms are ripped apart, nuclei shattered. Finally, everything, matter, energy, and the very fabric of space and time itself, is compressed back into the infinitely dense, infinitely hot singularity from which it all began. A final, definitive end. For decades, this Big Crunch held a powerful, poetic appeal. It offered a cyclical, almost metabolic vision of the cosmos, a universe that inhales and exhales, perhaps even rebounding into a new Big Bang. But in 1998, observations of distant supernovae revealed a shocking truth. The universe's expansion isn't slowing down, it's accelerating. This discovery, attributed to the mysterious dark energy, profoundly shifted our perspective. It renders the Big Crunch and its neat symmetry highly unlikely. Instead, this acceleration points us back to that first, colder, darker scenario, the Big Freeze. Our current data suggests this is the most probable path. An endless expansion driven by dark energy, a constant force, leading to a future of cold, dark, and eternal emptiness. And so, the ultimate fate of reality hinges on the true nature of this dark energy. If it remains constant, as we currently observe, the big freeze awaits. But if this dark energy is not constant, if it strengthens over time, a concept known as phantom energy, then the far more violent Big Rip remains a terrifying possibility. Ice, fire, or oblivion. 3 possible ends to a 13.8 billion year journey. We are a peculiar species, existing on a tiny planet for a fleeting moment, yet we dare to map the entire history of the cosmos, from its first femtosecond to its final, distant trillionth year. The universe may be destined for a cold, quiet sleep, a fiery collapse, or to be torn asunder. But for now, it is alive. It is filled with light, with complexity, and with consciousness. For us, in this brief, brilliant epic, the universe is not ending. It is. And our ability to comprehend this vast, cosmic story is perhaps the most extraordinary thing of all.